So let me mention, you may find something peculiar about the recording of Thursday's class. I assume some of you are using those recordings as study aids. There was a failure to record it, and the result was that I and one of the LAs came in on Sunday, and I completely redid that lecture with an empty classroom, but for the two of us. So if you miss yourselves on the recording of Thursday's lecture, you will understand why. I wanted to say some words about assignment 5. It is up. That's a section of it here. It's to find the center line, if you will, of bars, whether they're curved or straight. It has enough complications so that you better get started now. If you start it now, you'll be able to ask questions of me or of the LAs in time for you to finish. And one of the issues is that it requires you to take second derivatives. Any derivative operator, I'll write little d just for now, I have taught you should always be taken with an aperture, meaning you need a Gaussian with sigma applied as well as the derivative operator, right? So whenever you want to take a derivative properly, for example, of to get a derivative, and you want to do it in the frequency domain, you need to note that by the way, you understand that I'm using star, as is common in the imaging field, to mean convolution, and I'm using the x to mean, not quite x, but anyway, the time sign to mean times. And I know computer languages use star to mean the asterisk to mean times, but that's not how I'm using it in class here. Anyway, what you need to do is to think of this as, if you're going to go into the frequency domain, you take the DFT of f of I. In this course, I'm DFT of I. And in this course, that's done by this magnitude and phase transformation. What's it called? Amp phase something or other. It's in this. And then you need to multiply it in the frequency domain by the Fourier transform of the Gaussian. But the Fourier transform of a Gaussian is something you know from the formula, right? You don't need to apply DFT to get it. You know what this is from the formula. Moreover, the Gaussian is separable, which means a two-dimensional Gaussian is a one-dimensional Gaussian times in x times a one-dimensional Gaussian in y. And that also works in the frequency domain. So if you can, first of all, apply on all the rows the one-dimensional Gaussian, and then apply on the result in all the columns a Gaussian, and you get the effect of computing a Gaussian. And on the rows or the columns, the one-dimensional Gaussian's Fourier transform is known, right? And I showed it on the table last time. Okay, likewise, the formula for any derivative is known. In your particular problem, you're going to need the second derivative operator. Okay, and you're going to need directional second derivatives. And remember that to get a directional second derivative, you first of all compute the tensor. I'll call it d2i, but strictly it's d2 of g convolved with I, the Gaussian. And you you're going to take it in twice in direction v, that's what you learned in the very beginning of the course, that to take a second derivative in the v direction and the v direction, you do that. And that's going to yield you a 2 by 2 matrix of d2 by dx squared, d2 by dy squared, d2 by dx by dy, d2 by dx by dy, and everything in here is g involved with I. Right? And that's the matrix that you're going to do eigenanalysis on. And there's one of those for every single pixel. Each pixel has its own tensor. Right? So, back to what I was saying here. The first thing you should think about doing is to take the DFT and once and for all multiply it by your G sigma that is done separately. And you store that and use it multiple times after that. And you're going to need this Fourier transform of D for XX, you're going to need it for XY, and you're going to need it for YY. Right? So you're going to need it 3 times. And each one of them is going to produce, in the frequency domain, the derivative result, which after the inverse Fourier transform will give you respectively these 3 values, and this guy repeats itself down here. Clear? Any questions? Second thing to be careful about is, I remind you that this magnitude and phase program yields a non-square array. We talked about it in the lecture. And the problem is that, first of all, these positive index things in the array actually correspond to negative case of x and case of y, well, case of x in this case, negative case of x. And then there is this question, well, first of all, is 1 origin versus 0 origin, and is this 0, is this 1, or is that 1? You know, case of x equals 1, or this is case of y equals 1. Is it up here, or is it down there? Likewise, for x, where's the 0 frequency? So be careful that these kx and ky's that are the frequencies we're concerned in, you need to know where in the array, what the relationship is between kx and the array index, and what between ky and the y index in the array. And for me, the easy way to figure that out is just put in an image that's just same for all y, and it's just 2 pi times 1 over nx. So that's frequency k sub x equals 1 and k sub y equals 0, right? And just figure out where it's going to make 2 frequencies, one for a positive frequency and one for the corresponding negative frequency at kx equals 1. And so you'll know where kx equals 1 is in the array. And if you do the same thing for y, you'll know where ky equals 1 is, and you'll be able to work with it after that. The other issue is you have a bar, and you have a second derivative of a Gaussian cross-section, if you will. And this width is proportional to sigma. And you're trying to get a width that gives you the strongest result for a bar of particular width, and you need to know that ratio. The easiest way to find that is to build yourself a simple image that's pure horizontal bar or a pure vertical bar. If it's horizontal, then you'll know that the derivative you want is purely in the y direction, right? And then you'll try different widths and see which one gives you the strongest result at the middle of the bar. And then you'll use that ratio for your general input images, which will be like the snakes, right? That's a black bar on a, and these the kind of images you should be using for input are, well, except for the head, things that are approximately the same width all the way along the bar. Okay, and it should be a dark bar. You can use this image as one thing to try, but you should try it on other images you find that have that property. Yeah?
So will sigma be the same regardless of the image we're using?
Sigma will be the same ratio to the width of the bar.
Okay.
So if the bar is twice as wide, the sigma will need to be twice as big.
Gotcha.
And that ratio is what you'll need. And I would recommend that what you do is once you find that ratio from a simple bar image, that when you apply it on some other one, you try that sigma to bar width ratio, but you take a little bit bigger sigma and a little bit smaller sigma from that and see which one gives you the strongest result. Notice that sigma is a real number. It's not necessarily an integer. Any questions about this whole mess? The next thing I want to point out, and this was intimated in previous lectures, but now I want to be explicit. When you do convolution via the frequency domain, you actually have this periodic repetition thing that produces what we call wraparound. And so what that means is in both the x direction and the y direction, the image is understood to repeat itself. And so here, underneath it is another copy of this guy here, which is to say something that has this kind of intensity down here. And so if you're trying to compute the values up here of bar width, it's going to be a weighted sum of it and things near it, which are these guys down here. And so you should be aware that these edge effects are going to happen. So if you have a bar like this, you'll get a strong thing down the middle of the bar, but you'll also get a continuation down here of, as if the bar continued a bit down there, although realize that you're, what can I say, you're taking a weighted sum of what's really here and what's really here, and so it's going to be a less strong central line, but the central line is going to sort of continue till it dies out, if you will. And you're going to see this edge effect. This begs the question, well, how do I get rid of the edge effect if I'm going to do it via the frequency domain, right? And that's beyond the scope of this course. The short answer is, well, you only believe your results within some not close to the edge, within some part of the image, because you get these edge effects. But the alternative is, for example, to put some kind of a good collar around the image to extend it so that the edge effects don't get into the real image. So before you apply your convolution. A word about the word convolution. Revolution. What is the verb? To revolve, right? Evolution. What is the verb? To evolve. Convolution. Convolve. Please don't use convolute. It's not a word. Convolve. Convolution. Okay? Any questions about all of this? This will cement a lot of stuff that we've been talking about. The assignments are 4 after all. Yeah,
I'm not sure you're recording.
he's recording.
Okay.
Thank you very much for being concerned with that. But in fact, I'm not recording. The recording's going on by his computer. Okay, so why is convolution in the frequency domain so fast? Well, it's basically fast because there exists a divide and conquer algorithm for doing it. And for the divide and conquer algorithm to work, it needs three properties, all of which are held by the sinusoids. But there exist other basis images for which it also applies. But the three that are needed are they, first of all, for convolution, they need to be eigenfunctions of convolution. Well, they are, okay? The sinusoids are the eigenimages of convolution. Secondly, they need to be orthonormal. Well, eigenimages are orthonormal if the matrix that applies is symmetric, and it is for convolution. So they're orthonormal. Thirdly, they have to be separable, meaning you have to be able to apply it first in X and then in Y on the result. And that's true for the sinusoids as well. But there's one more property that's required. There are lots of things that satisfy 2 and 3, and that is that multiplicative decomposition at level of detail. Essentially what it comes down to is that e to the minus I 2 pi nu 1x times e to the minus I 2 pi nu 2x is the same as e to the minus I 2 pi nu 1 plus nu 2x. That is to say, there exist frequencies that when you take them, divide the frequencies in two parts, that the sum of two parts, you get the product of two other basis images. That multiplicative decomposition is not something I'm going to give you an exam on, but it turns out it's needed for the fast divide and conquer algorithm to work. And once you have that, it turns out that the name of the game turns out to be, I'll do it in one dimension. It's separable, so it works in the other dimension as well. It turns out that if you take the odd elements, 1, 3, 5, 7, up to n minus 1, you get something that's half as long as the original n tuple. And if you take the other, the even indices one, you can divide an array into two half-size arrays, one of which is made up of the odd elements, one of the even elements. And the way the divide and conquer, that's the division that the divide and conquer algorithm works on. That is to say, you apply the Fourier transform on this half, and the Fourier transform on this half, and then you combine them. And it turns out the combination is fast. Okay, combine those two results. And then the way these recursive divide and conquer algorithms work, well, how do you take the Fourier transform of this one? Well, you divide it into its halves. And all the way down to the point where you're taking the Fourier transform of a one-element thing, right, or a two-element thing. Okay, so the point is that there exists a divide and conquer algorithm here, and it, when applied to any array of capital N elements, runs in order n log n time. That's to say, roughly some relatively small number times n log n, where n is the total number of elements. In the case of an image, well, you can either think of the image as having n squared elements, or in 3 dimensions n cubed, where big N is, that n cubed or that n squared. Or you can think of the fact that you're doing it first on the rows and then on the columns, in which case n is the other one. It turns out, anyway, the upshot, but the number of times you do it, so for a 2D image, it turns out that it turns out to be order n squared log n in time. And for a 3D image, it's order n cubed log n, where we're here for an image that's n by n, and this for an image that's n by n by n. Okay. And all those n's don't have to be the same. It works for rectangular images too. Anyway, the upshot is I've told you now roughly why this DFT algorithm you're using, in fact, behind the scenes in this AmpPhase program, is so fast. And that much fast, rather than taking n to the fourth for n by n images or n to the sixth for n by n by n three-dimensional images. Yeah.
With the base things, how does the Fourier transform of one element of
Only one frequency, so it's the zero frequency, and that's just the constant. So the Fourier transform of 7 is 7. It's 7 times cosine 0, but cosine 0 is 1. Good question. Okay. If, on the other hand, your convolution kernel in the space domain is narrow, so this guy is size of the convolution kernel. So, for example, we have a little 3 by 3 kernel, m equals 3, or a 5 by 5 kernel. Then m squared may be a whole lot less than log n. And so it doesn't pay to go via the frequency domain. You can actually just do your weighted sums in the space domain, and it's faster. So for little tiny convolution kernels, ones that are not very wide, don't go via the frequency domain. And then you can take care of the edge effects without doing wraparound. Do something special at the end, at the edges, that if it falls off, the weights fall off the end of the image, you do something special like take the average of the other two along that row, if you're along a row, or some such like. Okay? So that just says in the special cases, in the special cases where the convolution kernel is 0, except in a very small array with m, then you should not go via the frequency domain. The next thing is the inverse DFT. I've already told you this, but this makes it explicit. The inverse DFT is the same as the Fourier DFT, except that all the signs on the exponentials are plus rather than minus. And that turns out to be essentially the same divide and conquer algorithm with one place in the program using pluses instead of minuses. Right? And so you will not find two programs, a DFT and a DFT inverse. You'll find one with a parameter that says either it's a forward DFT or it's an inverse DFT. And you set that flag, that parameter, and you get either the forward DFT or the inverse DFT. it follows from this that it's time for me to erase a lot. If you have convolution here, it turns into multiplication if you do it by the frequency domain, right? Element by element multiplication. But since it's true, because the way the inverse works, it's also true that multiplication in space gives you convolution in frequency. So if I have an image, I, that is I1 times I2 of x, then the Fourier transform of I is the Fourier transform of I1 convolved with the Fourier transform of I2. Right? So it goes in both directions. Or equivalently, the inverse Fourier transform of something that's a convolution in the frequency domain is simply the product of the Fourier transforms of the respective things that are being convolved. Okay? I've said everything that's here. This just emphasizes that if you have some kind of a mixed derivative, you can have so many derivatives in the x1 direction and so many in the x2 direction and so many in the x3 direction. You have n1 in the first dimension and n2 in the next one and n sub m. Then what happens is, because these are cascaded operators, that one is applied to the next. So if you first apply, say, dn m of xm, one time you'll get a 2 pi I nu sub x sub m. And you apply it one more time on x sub m, and you get another 2 pi I nu x sub m in the frequency domain, multiplying. And then you do that n sub m times, and you get 2 pi I x sub n x sub m to the n sub m power. And now you apply the n sub n minus 1, and you get another 2 pi x sub n minus 1 to the m minus 1 times that, and so on. And so you can build up a whole big kernel by all these successive applications of each 2 pi I x sub k, 2 pi I nu sub x for each first derivative of which this cascade is made up. The last thing I want to specifically point out, I've intimated it many times, and that is, if you have a particular shape which is in an image that you're looking for in some target image, the optimal thing to do is to use the very shape, that image, as a kernel. So you let h of x be your target. And now if you have an image here and you're looking for this particular shape, I can't repeat the drawing very well, but anyway, this is supposed to be the same shape as there, and it happens to be somewhere else in the image, and it's oriented the same. I didn't make that either. But if you apply this kernel on this image has a bunch of other stuff in it, and different background and whatever, it'll get very, very big right at the center of that place. The result of that convolution is called matched filtering, right? And that's basically, I've already said, why these specific derivative of Gaussian operators do their job. The first derivative of the Gaussian looks like an edge, right? It has a zero background, then it drops down. It drops here along an edge in a sort of slightly smooth fashion. Likewise, this guy here looks like a bar, right? It's bar that way. It's got these little side lobes, but nevertheless, the main feature is bar-like. And so essentially what you're doing when you're using these derivative operators is using them as match filters. Be careful, though, because when you're really doing match filtering, this guy's not going to pick out something that's a different angle. It's not going to pick out something that's a different size. It's not going to pick out something that's a different width. It's got to be just the same target if you're going to actually do match filtering. Or else you have to do special things to normalize for size or orientation. And we're not going to talk about that in this course. I'm done with all the basic stuff on sinusoidal decomposition. Right, we've learned that it's good because the sinusoids are the eigenimages of shift invariant linear operators, that is to say, of any convolution. And it produces a very fast algorithm for applying those shift invariant linear operators. And there's so many of them that we want to apply that that's really good stuff to know. We're going to go on now to another application of understanding, and that is, I'll call it pixelization. The idea is, if you have a camera and it's producing some very large thing, let's say a 10,000 by 10,000 pixel image, right? That's going to take you, in the computer, 10 to the 8th words, right? And if it's 3D, it's going to take, and it's square, it's going to take 10 to the 12th words. And while we have lots of memory these days, that's too big to want to store, right? And so, why not make it into you've been doing it already to make it into 128 by 128 images, but maybe you should make it into 256 by 256, or 512 by 512, or what? The question is, what's the right spacing to store these images without losing too much information? Or put another way, what's the right size pixels? Or into 3D, what's the right size voxels? And that's what this next topic that we're going to be covering. And so I want to make sure you understand that the first thing that happens when you want to pixelize from a essentially continuous image, it could be digital with lots and lots of pixels, or it can be actually continuous, is you want to think of it dividing it into little squares or little rectangles. And in each rectangle, the result that you want is going to be got by averaging over the rectangle, or more correctly, integrating over the rectangle. And that integration is, you're summing up all the photons that come out in that rectangle, if you will. And then, at least for these rectangles, for each one of these rectangles, you're going to want to take the center pixel of each one of these rectangles. Now, strictly speaking, this integration only has to take place at, if you're producing an n by n image, at 4 n by n rectangles. But because integration is a shift invariant linear operator, it's cheaper for us to run it for every possible rectangle. Okay, so you'll also be, for example, getting it for this rectangle, which isn't one of the ones you ultimately want. And you're just going to do a convolution with this rect function, right? Rect is the averaging, is the integration operator. So what we're going to do is we're going to convolve the image, the input image. Write it in a darker pen so that the recording works. Where the averaging, the non-zero part of the rect is in a region that's delta x by delta x. Or if in the case of non-square images, it's going to be delta x by delta y, right? That averages, if you applied that, then you would have an image where you have what's called a running average, or a running sum. That is to say, at every pixel, at every place in the image, you would have this as if it was a pixel. As if it was a pixel width. But you'd only want ones of those, and so we're going to pick out the center values. And that's going to be accomplished by multiplying by a comb function, which is 0 everywhere. More precisely, a brush. Right? And if it's going to be delta x in the x direction, delta y in the y direction, if necessary. But you got to be careful about, because the comb is a bunch of impulses. But be careful, because if you think of combs of delta x, if delta x is one level and delta x prime, a different delta x, is half of the other delta x, you're going to have twice as many impulses in 1D, 4 times as many in 2D, 8 times as many in 3D, right? And that's not what you want if you want to compare different possible sampling schemes. So in one dimension, it turns out you have to multiply, to compensate for that, you have to multiply by delta x. So the one dimension, okay, so in one dimension, it's going to be delta x times combs of delta x. This is in one dimension. And if it's in 2 dimensions, it's going to need to be a delta x squared. Right, in 3 dimensions, it's delta x cubed. Okay, but the point is, it's instead of a comb function, if you want to compare different pixelizations, you need to get everything comparable, and that means that the function you want in 1 dimension is going to be this thing, delta x to the m times a comb. And a comb is a sum of delta functions at all the different integers. Okay? Integer multiples of delta x, to be more precise. Okay, so what do we have? We have, this guy's a time sign. Just to make it a little bit clearer, I'm going to put a dot here so you don't confuse it with an x, but that's times. And what we're interested in is what's the effect of this pixelization, which consists of averaging or summing, integrating over the pixels of voxels, and then sampling the result. Okay? And the answer is, it's understood much better in the frequency domain than in the space domain. So let's look in the frequency domain. And so we're going to be interested in the Fourier transform of this whole thing, which is convolved with a rect and multiplied by a brush. Well, we've already seen what's going to go on. The Fourier transform of this product is going to be the convolution of the Fourier transform of this side and the Fourier transform of that side. And the Fourier transform of a comb is another comb with spacing 1 over delta x rather than delta x. Right? In frequency, the spacing is the reciprocal of the spacing in the space domain. So, and the Fourier transform of this thing, okay, so is Fourier transform of I convolved with rect convolved with the Fourier transform of this guy, which, if you go back to our thing, drops the delta x thing and just turns out to be comb sub 1 over delta x of nu. The Fourier transform of delta x comb in 1 dimension, or delta x squared comb in 2 dimensions, or delta x cubed comb in the 3 dimensions, is simply unmultiplied comb in the frequency domain. And of course, what's the Fourier transform of the convolution of this thing? Convolution of 2 functions, the Fourier transform of it is multiplication of the 2, right? So we're going to get Fourier transform of this times the Fourier transform of that. And this guy, you know, is a sinc. Right? It falls like 1 over nu in the frequency domain. Okay, so let's look at this whole thing here. And in the slides, that thing is called G. Don't confuse that with the Gaussian. It's just some function that I need a name for. And I'm going to call that G of nu. And so this is G of nu convolved with a comb. Well, what does that do? Well, a comb have spacing here. Okay. Okay, the point is the comb at spacing delta x. There's one at 0. There's one at 1 times 1 over delta x, 1 meaning an impulse. There's an impulse at 2 times 1 over delta x. There's an impulse at 3 times 1 over delta x. Likewise, there's one at minus 1 over delta x, minus 2 over delta x, all the way to infinity. Right? And I remind you that convolution replaces the this is convolution in the frequency domain, but this is new that I'm drawing. Replaces each impulse by the thing that's the kernel centered at that place. So if G looks like that picture, one of these here, that's G. That's my example of AG. Okay. It may have negative parts, and in fact, it's the Fourier transform of something may be complex. Okay, but I'm just acting as if it were positive and real. It's not. We'll come back in a moment to see what happens when it's not. But the upshot, it's replacing each one of these guys by the corresponding G kernel. So the upshot is you get a repeated G's, one for each one of these impulses, the same. And the result is the superposition of all of these. A shifted G by 1 over delta x, another shifted G centered at 2 times 1 over delta x, another shifted one at 3, one centered at minus 1 over times 1 over delta x, and so on, right? And all these add up. And so you get some periodic looking function with the period of 1 over delta x. That's the sum of all these G's. Yeah.
Do we not transform the comb function?
This is the transformed comb function. This is the comb function in frequency, but the comb function in frequency is the Fourier transform of a comb function in space.
So why would you the comb function is already transformed?
Yeah, that's why I wrote new here and not x. Yeah. Easy to confuse because it's a comb function, but with a reciprocal spacing from what it was in x. Okay, so another way of saying this is I only need to know one period of this. Right? A period is with delta x. So let's look at one period of it. And that one period is going to go from 1 over minus 1 over 2 times a half times 1 over delta x to plus a half 1 over delta x. Okay, that's an interval of width 1 over delta x. That's the period. Centered at 0. And anywhere else it's the same because it's just periodically repeated. Right? So all the information I have from my sampled image is in this one interval, new in this. And this is in one dimension, and 2 it's going to be delta x by delta, 1 over delta x by 1 over delta y, and so on, right? What's the information that I have in that interval? Well, the answer is, whoops, at this frequency, so here is, the h here is what I'm calling delta x there. So here is our interval from minus 1/2 here, 1 over delta x, to plus 1/2 1 over delta x. And at any frequency here, what you have is the sum of the contribution from the 1 to 0 and the contribution into that interval of 1 into that interval of the 1 at 1 over delta x over, and the contribution at 2 of delta x to that, and the one from minus 1 over delta x. The other ones, besides the ones centered at 0, are polluting the information that came from the main G that we cared about. So the trick is somehow make the interval so that these guys are pulled apart. So instead of being overlapped, what you want in the frequency domain is, here's your G. If your spacing is like so, so you want 1 over delta x's that are better. You want 1 over delta x's such that there's negligible contribution from one copy of G. This is G again, but offset. This is G again, but offset in frequency. And you want this guy to not pollute that guy, right? Because then when I just add everything up, I will get, here's my interval from minus 1/2 to plus 1/2, 1 over delta x. And that interval in there will have the Fourier, everything about the Fourier transform of the original kernel, G. And I can restrict myself to that interval. Well, how do I restrict myself to that interval? I simply multiply in the frequency domain by a rect. And 0 outside that minus 1/2, plus 1/2. And now I've got everything I needed to know about G, and now I can take the inverse Fourier transform of that. I'm in fat safe. In other words, I haven't lost any information about the original image if I organize my delta x to be band limited between minus 1 over 2 delta x to plus 1/2 1 over delta x. If I can choose a delta x so that I'm band limited, that is to say my original image has no frequency component, 0 at all frequencies above 1 over delta x, plus 1/2 1 over delta x, and minus 1/2 1 over delta x, then I can completely reconstruct my original image from the pixels. Okay? I haven't lost any information if I can solve this. Well, you got to be a little bit careful because what's leaking in from the right are these left lobes, the left side most strongly. And what's leaking in from the right into this interval are the right sides of this. And the left sides and the right sides, oh, remember convolution, remember frequency domain transformations has this complex conjugate. So the right side stuff, the negative frequencies produce a complex conjugate of the right side stuff. So you have the leaking in of this piece is complex conjugate of this, what's in here, and this guy is the original thing, and so on. Anyway, fine, you take care of all of that, but to make a long story short, the name of the game is to try to choose your delta x, so the Fourier transform of I is negligible outside those. Now, one term that we need to be careful about, because this is often described, is that it turns out, I remind you that the sinusoids are periodic, and so we've talked about that. And so what happens is that a sampled high frequency sinusoid, when sampled, just you looked at the samples, has no different values than one with coarser samples. The reason that this is happening is because the contributions of this G that are outside this minus a half to plus a half times 1 over delta x, ones that are outside this interval, when they're sampled, act as if they're inside. They have the very same sample values. We say there's an aliasing. Something with high frequency is aliased as if it were low frequency once you do the sampling. And so you can understand it in terms of this math that I've done that's, I find, much more informative, that says it's this repeated version of the same function, of which we're only interested in one particular subinterval. But then you understand that the reason there is pollution is that these higher frequency components in the image are polluting the lower frequency, the values at the lower frequencies. And the idea is to make a delta x that is a 1 over delta x that is large enough so that you get negligible pollution. To say you'll get no pollution is probably unreasonable. But once this G function has fallen far enough, you're willing to put up with a little bit of folding. Okay, so this one way of thinking of what's going on is that at this place, this guy folds back in, tips over and folds back in. So it comes, you can understand it as this. If this is the 1 over x, then this guy appears over here. And this guy appears over there. Right? It folds back. That's because it's really coming from the other copy. But it can be understood as a folding, except the folding comes with complex conjugation. Yeah.
Could we also use a sine graph squared?
Can you use a sine graph?
A squared sine graph? What if we not have open?
Well, sine graph is just another way of thinking of the Fourier transform. So, yeah, the answer is yes, if that's your favorite way of looking at things. In any case, if this guy really looks like this, then it folds back again. Whoop, folds back again. It folds back and back and back. And so this frequency 1 over half times 1 over delta x is called the folding frequency sometimes. Right? It's the frequency plus or minus it causes the Fourier transform of the image to fold. Well, fold, yes. Come from the next copy is a slightly better way of thinking about it, but either way. Okay. So that's what this says. That you think of it as folding. And that folding frequency also gets the name of a mathematician who figured this out, who was, I guess it's a Swedish person, at least it's a Swedish name, named Nyquist in English, Nyquist in Swedish. Quist means twig, if anyone cares, and ny means new. So this guy's named Newtwig, but okay. Anyway, Nyquist frequency, folding frequency, 1/2 of 1 delta x. Okay, but I remind you that our objective here is to choose a good delta x, right? And so if you want a big you want a large a large folding frequency, that corresponds to a small pixel spacing, delta x. So if you tell me what the folding frequency 1/2 delta x is, half of delta x, well, I can multiply that by 2, and now I get delta x, and I take it, 1/2 delta x, and take its reciprocal, and that gives me delta x, and that's the spacing I want when I'm doing pixelization. And so I basically I've answered my question. What's the right pixelization? Well, it depends on the spectrum of the image, on the Fourier transform of the image, and at what frequencies it falls. Why is it going to fall at all? Well, because images come from cameras, and cameras blur, and blur means convolution with something that falls in frequency. And so you're going to absolutely have some place that falls, and it depends on the resolution of the camera what your folding frequency should be. And so it's not going to be too surprising if I tell you that if my camera has a impulse response function, an h, that's like so, and it's some function like this that has some sort of a width, half width here, like that, then the corresponding Fourier transform, which you're multiplying by in the frequency domain, is going to have a width that is inversely proportional to this width. We've seen that happens for Gaussians. It happens for general H, and for these cameras typically have these unimodal single maximum impulse response function. The farther away you get from the point, the less the effect of that intensity is. And so what about this W that we're going to use? And we're going to use something called the Rms Width. And I got to tell you what Rms Width is. But the main point is that for a Gaussian, the Rms width is just sigma, the standard deviation of that Gaussian. Okay? And so RMS stands for root mean squared. Take any function at all and think of it as f as a function of x. Right. What I'm going to do at any f, I can calculate the width of that function. Right, so now I get a width that is a function of f. And I'm going to square that. That's the squared part, the squared width. And then we're going to take the mean of that. Zero to, well, call this, get some sort of another variable, little g, let's say. Okay, so that's the mean. I take the mean over all widths squared. And that gives me something that's squared looking, and then I take the square root of that. That's the root part. So it's the square root of the average square width. That's what root mean squared means. And if you do that for Gaussian, you'll see that that turns out to be just sigma. But you can apply that calculation to any kernel. All right? Okay. So what I've said is we can think of these G's as having width. Let's go back to our handy dandy table. There it is. If the kernel has root mean square with sigma, then the Gaussian up here in the frequency domain is going to have root mean square width 1 over 2 pi sigma. Right? It's reciprocal except for this multiplication by 2 pi. And so now I know what the widths are going to be of any eye that came from that camera. It's going to have been multiplied by this guy in the frequency domain with width 1 over 2 pi sigma, with RMS width 1 over 2 pi sigma. And so, assuming my image is there's no bias to its frequency. That is to say, sorry, my scene. Assuming my scene is likely to have any frequency at all, equally likely, and that turns out to be about true for most of the images you'll deal with after multiplication by this camera transfer function. They will all have fallen from whatever the zero frequency is to something having to do with the ratio of this value to this value. Each of them being on average, over the population of possibilities, having been multiplied by the same base image intensity. Okay, so we're going to be interested in this ratio to that ratio. The frequency zero behavior of our transfer function. How much it has fallen off, because how much it has fallen off after when you get to the Nyquist frequency, how much has fallen off is going to determine how much pollution you have. And so a reasonable thing to do is to say, well, this is the amount that's going to be folding in at this folding frequency. And all the other copies are going to be so far away that they have a negligible contribution, right? And likewise on this side, same thing. And so it's the ratio of this to this in your transfer function that basically determines the amount of pollution you're going to have. Once you make that assumption, the final thing you want to decide is, well, how much pollution are you willing to have? Okay, so if I have some epsilon, which is the relative value of this to this, that I want to be willing to endure, if I tell you I'm willing to, for epsilon to be 0.01, that is to say this guy should have fallen from whatever it was at 0 to value 0.01 of that, not 0.01, but 0.01 of the 0 frequency. If I tell you an epsilon, I can figure out what the sampling should be. And this is what it comes out to be when you do that analysis. It says that delta x should be pi times the width in the frequency domain of your impulse response function of your camera divided by the square root of this interesting thing, which is twice the natural log of the ratio of 2 to pi epsilon. Okay, so you write that down and you put it in your notebook, and every time you want to decide a spacing, here's the formula. You go find your impulse response function, find out what its sigma is, what its Rms width is, and that'll tell you the delta x that you need to endure epsilon per fraction pollution. All this business was discovered by an impressive scientist named Shannon, Claude Shannon. It's called Shannon's sampling theory. Shannon was a pretty amazing guy. He was a grad student at MIT. This was his master's thesis. Okay. His PhD, by the way, he invented information theory. Pretty right kid, pretty strong scientist, right? Anyway, fine. So notice, by the way, that in this formula, as promised, delta x is proportional to sigma. And the proportionality factor is pi over that square root that's there. Questions? It follows what the last line. If you take an image and now you're going to apply another h to it, a computational h, because you want to lower noise or whatever, you're going to apply some other filter, or if you will, kernel. Well, the new h is the convolution of the camera's h and this computational h, which is going to have a bigger sigma, right? You convolve like two Gaussians and you get a wider Gaussian. And by the way, it turns out that if you take one Gaussian and you convolve it with another Gaussian, the overall result is a Gaussian, and its RMS, well, its mean square without the R, with value sigma squared, is just the sum of the squares of the sum of the mean squares of the two. So this is a useful little formula. But so now you get a wider sigma. So what? Well, so what? You can use a smaller, a larger spacing, fewer pixels, right? If I have a camera thing of some width and then I convolve it with another thing of the same width, I'm going to improve my sigma by square root of 2. That means I can make my spacing wider by a factor of root 2. And so if I needed a 512 by 512 image to satisfy all this other thing on the original image, and now I'm going to apply this other computational convolution on it, I don't have to compute my result at the same spacing that I started out with. I can let the spacing be root 2 bigger, by factor of root 2 bigger. I can save memory space by sampling more coarsely. And that can be pretty beneficial. Okay, so next time I'm going to just talk about the word anti-aliasing, and then talk about what's good about the Fourier basis. But now we're going to emphasize what's bad about it. And then once we see what's bad about it, we're going to talk about, well, maybe if we don't want to endure what's bad about it, what should we do? We should use different basis images. And we'll talk about that starting next time. Till then. Remind you, I have